SwayamPrabha. Digital India. Educated India.
Hello and welcome to the 8th lecture of the course on machining science. So, I will remind you that in our last session we started discussing the merchant circle diagram, and we said that merchant circle is the circle which is drawn with a diameter of r or r prime, which is the resultant force acting on the chip from the rake face from the tool through the rake face or to the chip from the shear plane of the process. So, if we do that, in this case the components of these forces, that is the cutting force, thrust force, shear force, normal to shear force, friction force and the normal force, the tips of these components will be lying at the periphery of this circle. So, we have shown this circle. This is the merchant, this is known as the merchant's circle. From here, knowing that these are the angles phi, this is the shear plane angle, this is the rake angle and this is the friction angle, we can correlate the Fs, Fn, Fc, Ft, F and N with the resultant force and the angles, these three angles. From here, that we have derived last time, from here we can find out that, let us say, from the Fc, R is equal to Fc divided by cos of beta minus alpha, which is also equal to, from here, Fs divided by cos of phi plus beta minus alpha. This is what is written here. So, therefore, from here Fc, which is the cutting force, this can be found out as the Fs into cos of beta minus alpha, it goes in here, divided by cos of phi plus beta minus alpha. So, this is the component Fc that we can find out by this way. Here that does mean that if we know Fs and if we know the friction angle, shear plane angle and the rake angle, we can find out analytically the value of the Fc without having anything, without machining analytically. Now, here Fs is very difficult to find out because we can measure the forces during the machining process, and through the measurement we can measure only the Fc and the Ft. Okay. So, to find out the Fs, we can say that shear force Fs along the shear plane, this can be written as the Fs is equal to stress into area, force is equal to stress into area, and the area of the shear plane will be width of cut, uncut thickness divided by sine of phi. So, this you can find out from the diagram, okay, and this has been known. For example, if we have the diagram this way, all right, this way. So, this is the shear plane, here is the tool, all right, and this is the angle which is the phi, and this is the value, this one from here to here, this is called the uncut thickness, all right. T1 is the uncut thickness, because this is not yet cut, that is what we said, and this thickness is the chip thickness, which is called the T2, going ahead I am telling you. So, T2 is the chip thickness, all right, chip thickness. Now, this then therefore, the area of the shear plane, this shear plane can be found out if we know, for example, this is the width of cut, okay, and into this will be into T1, which is projected here, divided by sine of the phi. From this diagram you can find out how the Fs can be found out. This is the area of the shear plane and this is the stress. Now, the tau s is basically nothing but the strength of this material, workpiece material, which is tau s. Now, this here it is written T1 is the uncut thickness, W is the width of the workpiece, and tau s is the shear strength of the work material. Okay. So, therefore, Fc, if we put these values, it can be found out by W T1 tau s by sin phi, which is this, which is Fs into cos beta minus alpha divided by cos of phi plus beta minus alpha. So, therefore, if we have the Fc, which is the cutting force component, we can find out the power, which is, as I said earlier, which is a product of Fc and the Vc. Fc is this cutting force, Vc is the cutting velocity, and Vc goes like this. This is the direction of the cutting velocity vector. Now, as per nature, taking path of least resistance, during cutting, phi takes a value such that least amount of energy is consumed or P is minimum. This means that during the process, the cutting process, by nature, the phi or the shear plane angle, it adjusts itself in such a way that for the entire process the minimum consumption is, minimum power is consumed. This is the natural process, like in nature everything goes to the least resistance. Okay. So, therefore, in here also it happens so that the phi adjusts itself so that the minimum power is consumed or the P remains minimum. So, if we say that P is a function of the phi shear plane angle, then this will be constant. Okay. This numerator will be constant divided by, because there is no phi, that is why it is constant, because we are taking with respect to phi, all right, and a function of the phi, divided by this has a phi. So, this in the denominator we have the sin phi and the cos phi plus beta minus alpha, all right. Now, for least energy, for the minimum energy, the first derivative of this P phi has to be equal to 0. So, we will take the denominator. Okay. Now, what we are saying is that the power has to be minimum, that means this has to be maximum, all right. For this to be maximum, the first derivative of this or the denominator has to be equal to 0. Okay. So, if this is maximum, so then the P power is minimum. So, for this maximum we have taken the first derivative of the denominator and we have made it with respect to phi, this is equal to 0. So, if we do that, sin phi cos phi plus beta minus alpha, the first derivative is 2 phi plus beta minus alpha, this is equal to pi by 2. Okay, this you can find out, you take the derivative of this with respect to phi and this will be the 2 phi plus beta minus alpha is equal to pi by 2. This is known as the Marchant's first equation. But if you have to always keep in mind that this equation is valid only when those 8 assumptions that I have shown in the last slide, for example, these assumptions, they have to be satisfied. If any of these assumptions is not satisfied, in that case the Marchant's first relationship is not valid. This you have to keep in mind all the time. Okay. Now that we found out the Fc, we can find out the shear stress as Fs divided by As, okay, and the As, which is the area of the shear plane, that we have already seen that this is W T1 divided by sin phi. This is the area. Area is equal to width into the length. Length is T1 by sin phi. I have already shown it to you. So, width into length is that area, and therefore, the tau can be, or the shear stress can be found out by Fs. We have found out already that Fc cos phi minus Ft sin phi into the sin phi, it will go here divided by As, okay, and in the denominator it will be W in the into T1. Okay. Now, this is the shear stress that we can find out analytically in this way, meaning that here why I am saying that it can be found out, because as I said that when you are measuring the cutting forces in the in the machining zone, you can measure the FC and the FT through an instrument, as you know that this is called the dynamometer. We will be discussing that little later. So, if we know the FC and FT, and if we know the phi, if we know these are the parameters which are the physical parameters, this will be knowing. So, therefore, the tau can be known analytically by knowing the FC, phi and the physical parameters as width of cut and the uncut thickness. Okay. Similarly, we can find out the normal stress, which is Fn divided by Fs, like we have done it here. This was Fs by As, and this will be the normal force, because it is the normal stress. So, therefore, the normal stress can be found out by putting the value of Fn. Fn, if you see from the Marchant's, we found out as Fc sin phi plus Ft cos phi. This will be multiplied by this As, where sin phi is going up and the Wt1 is here. So, the normal stress analytically can also be found out if we know the Fc, Ft, phi and the physical parameters as width and the T1. This is the advantage, that when you do not have the cutting process, analytically you can find out what is the Fc, what is the Ft. So, the advantage is that when you are designing the machine tool, you do not have the cutting process, but you have to make the machine tool where you will this machine will be capable of removing this much material or providing this much power, for example. Okay. So, you have to select the prime mover for that machine tool. Now, the power of the prime mover has to be little more than the power which is consumed during the machining process. And the power consumed during the machining process can be found out by the product of Fc and the Vc. Fc you can find out analytically from the Marchant's, as we said, and the Vc is you are giving that Vc, because Vc is the pi into d into n. D is the diameter of the workpiece. So, if you know that you have to machine a workpiece of a certain diameter and with a certain revolution RPM, then you will be knowing that what is the power it will be consuming if we can find out analytically the value of the Fc, which is the cutting force. Okay, this is clear. Next is that how we can find out the shear strain in the chip formation. So, as you understand that the shear strain, I have shown it to you earlier, that suppose if you have a piece of material like that and this has been deformed, for example like this, okay, by a shear force or the shear stress which is applied. Now, this movement because of the shear stress applied is x. I am repeating that, I have already shown it to you earlier, and this is suppose that was probably B, all right. So, the strain which can be denoted as this is the x divided by B. Okay. So, this is the strain occurring when we have the tau applied, and because of the tau we have the movement of the material, permanent movement, which is a permanent, that is a plastic deformation, as x, and the distance between the two these layers will be B. So, similarly, in case of machining, you can actually assume that this chip which is flowing, the chip which is flowing along the rake face of the tool, this can be assumed as a stack of cards, for example. Okay. Let us say each card is a layer of the chip which is flowing along the rake face of the tool. Now, when the force is applied from the tool, this stack will be moved, and it will be moved like this, as it is shown in this diagram. All right. Now, here what you can see is that this is the movement which is equivalent to the x that we have shown, all right, and the distance between the two layers will be perpendicular to that, okay, perpendicular to this line and this line. Now, therefore, if we actually draw this triangle, this triangle will be given as this. Okay. This is the, let us say B, this point is A and this point is C, all right. So, A, B and C, here this is the movement, which is let us say equivalent to x. x is here, all right. So, therefore, A and C is the movement of the material because of the shear stress which is applied from the tool, and the distance between the two layers, distance between these two, that is equivalent to B, will be if we draw a normal from the point B to AC, which is let us say at intersecting at D. So, BD is normal to AC, okay, and this is the 90° angle. So, therefore, once again this is the triangle which we have taken from here, with AC is the movement equivalent to the x because of the shear force, which is shear force or shear stress which is applied from the tool, and therefore, we can say that the strain which is AC, that is x, all right, AC is equivalent to x divided by B, which is the B equivalent to BD. So, AC by BD is the strain, and AC is equal to AD plus DC, okay, divided by BD. So, this can be assumed as AD by BD plus DC by BD, and from here you can see that this is the angle which is rake angle, which is here, and this is the angle between the AC and this, that is the AB. What I mean is that this angle is phi, right, meaning that this is the angle which is phi, shear plane angle. This is the same angle as in here also, because this line and the AB is parallel, this is intersecting. So, this is phi, shear plane angle, this is shear plane angle. So, therefore, this angle will be phi minus alpha. Okay. So, therefore, if you see this, which is equal to tan of phi minus alpha, which is AD by BD, all right, AD by BD, and DC by BD will be cot of phi, because BD by DC is tan phi. Okay. So, therefore, it will be cot phi. So, now we can find out the strain if we know the phi and the alpha. See, this is as easy as that, meaning that analytically you can find out how much strain will be required for machining a particular material if we know the phi, and alpha is known because we are using a tool where we will be knowing what is the rake angle of the tool. Okay. So, we have to know the phi only, so to find out what is the strain involved in here. Okay. Now, let us see that how strain rate can be found out. Strain rate, there is a time component. So, strain rate is delta S by delta Y. Okay. This is the same thing as in here, that is the strain, this one. Okay. Let us say this is this, there it is said to be delta S, and this is delta Y, okay, equivalent to delta Y. So, delta S by delta Y is the strain, this is the strain, okay, and this is happening at the delta t time, meaning that this movement of delta S or x, these are equivalent, this is happening at a time delta t, all right. So, therefore, the strain rate will be strain into 1 by delta t. Now, this can be found out if we have the diagram here. See the rake face of the tool, chip is flowing along the rake face of the tool, and the chip velocity is here. So, the shear velocity is along the shear plane, and cutting velocity is here as we have shown there earlier. So, therefore, if we join them, let us say this is the direction of the chip velocity, this is the direction of the cutting velocity, all right, and the direction of the Vs is along the shear plane. So, we have the VCH, VC and the Vs, and we know the angle because between the Vs and Vc, here this angle, we have seen that this angle is phi. Between the VCH and the line perpendicular to Vc is the alpha. So, this is alpha. So, therefore, this is 90 minus alpha, and this is the 90 minus phi minus alpha. So, if we have this triangle, we can use the sine rule and we can find out that V s divided by sine of this angle equal to V c divided by sine of this angle equal to V c h divided by sine of this. That is what we have written here. V s divided by sine of 90 minus alpha, which is the cos alpha, equal to V c divided by sine of 90 minus phi minus alpha, which is cos of phi minus alpha, equal to V c h divided by sine phi, because this is the 90 minus this thing, V c h divided by sine phi. So, therefore, the shear velocity V s we can find out through the V c as the V c sine of 90 minus alpha divided by sine of 90 minus phi minus alpha, which is the cos phi minus alpha. And the shear velocity, once we found out, see, if we write the shear strain rate in this way, so delta S by, you can write it in the form of delta S by delta t into 1 by delta y. So, delta S by delta t is nothing but V s, which is the shear velocity, and this is divided by V delta t. So, we will write it in this way, that this is equal to delta S divided by delta t into 1 by delta y. So, delta S divided by delta t, this is actually V s or the shear velocity, okay. And this is into 1 by delta, sorry, here it will be delta t, okay, delta S by delta y, yeah, sorry, here it is, I am sorry, this is delta y and divided by 1 by delta t. So, this is equal to V s, delta S by delta y, and this is divided by delta t. So, therefore, strain rate we can find out if we know the shear velocity and the time at which it is actually taking place, delta t. We will come in details in the later stage. So, now let us see that how the shear plane angle can be measured, because as you understand that all the time what we were telling is that we can find out analytically the value of the FC if we know the phi particularly, because all other angles will be known, all right. So, therefore, making of the phi or finding out of the phi, this is the shear plane angle, is very important. Now, the shear plane angle can be measured, okay. Shear plane angle is measured in this way, that this is a device which will actually make a partially formed chip, all right. So, for example, here this is the device where you have a cylinder, and this cylinder is fixed in here with a pin, shear pin, meaning that if the cylinder is pushed to this side, the shear pin will be broken and this cylinder will come forward. It is stopped here by the shear pin. On the cylinder there is the workpiece for which you are trying to find out the value of the phi, which is the shear plane angle, and behind this there is a device where you have the tool, and at the back of the tool there is a tongue or a surface, okay. So, if it is moving forward in this direction, the direction of this workpiece, in that case the tool will touch the workpiece before this shoulder, and therefore, as it is coming in contact with the tool, the shoulder is still at the back, it is still not touching this, okay. So, this will actually remove a part of the material, and then this shoulder will come and hit the cylinder. So, in that case abruptly the cylinder will come to this side, it will be broken, and we will get the workpiece with a partially formed chip like this. So, now if the workpiece is graduated like this, all right, we can find out that how these graduations have been deformed, and then we can clearly see a line through which the deformation has gone, and if we join these points, so we can find out, we can measure under the microscope what is the value of the phi, which is the shear plane angle. Of course, this is not a very accurate measurement. there can be faults, there can be errors, and therefore, normally the shear plane angle is determined analytically, and that is also a very easy process. For example, here if you see the diagram, we have the tool here, and this is the rake angle, all right. This is the shear plane angle that we have seen. Now, this angle, if we see between the line here SP and the SN, which is the perpendicular to the rake face of the tool, okay, this angle is also alpha, that is the shear rake angle, because this line is perpendicular to this line, and this line SN, which is perpendicular to the rake face of the tool. So, between these two lines also the angle will be the same as in here, which is the rake angle, all right. Now, if we have this diagram with the T2 as the chip thickness and T1 as the uncut thickness, then the chip thickness ratio concept is there, which is the ratio of the undeformed chip thickness by the chip thickness. So, normally in practice it has been seen that this is roughly between 0.6, 0.5 and 0.6. Okay. That means, after deformation the chips becomes wider, okay. The thickness becomes more, almost 2 times, right. This is 1 by 2. Now, chip thickness ratio is the ratio of T1 by T2. Now, T1 from this figure you can find out that this is OS, okay, OS into sine of this angle, all right. So, this is the T1, therefore, T2 similarly from this triangle you can find out that this is OS into cos of this angle, and this angle is the phi minus alpha. Okay. So, this angle is the phi minus alpha, this is the angle, all right. Now, this once again OSN, this is the triangle, there you find out that the T2, which is this SN, this is equal to OS, this shear plane, and the cos of this. So, therefore, the chip thickness ratio can be found out as T1, which is OS sin phi, divided by T2, which is OS cos phi minus alpha. OS is cancelling, sin phi by cos phi minus alpha is remaining, and then we can find out that 1 by this chip thickness ratio is equal to, you can inverse it, and from here you can find out that the tan phi is equal to the chip thickness ratio cos alpha divided by 1 minus chip thickness ratio and the sin alpha. Okay. So, from here, as you understand that analytically we can find out the value of the phi, which is the tan inverse of this chip thickness ratio, let us say we know, okay, and the cos of alpha we know, because this is the tool that we are using, 1 minus chip thickness ratio we know, and this is the sin alpha. So, this is the way we can analytically find out the value of the phi rather than measuring it, because measuring will be not very accurate, all right. So, as you can see here that from the Merchant's diagram, starting from the Merchant's diagram that we found out the FC, we found out the values of the FT. After that we can find out the shear stress, normal stress, okay, with these values, because here the stress it will depend on the FC, FT, and this phi now we found out analytically. So, analytically now we can find out what is the value of the shear stress. Similarly, we can find out the normal stress by analytically finding out the phi, and we know the FC and FT, all right, and we can find out the value of the normal stress. Similarly, we can find out the value of the shear strain, because now we know the phi, this is the shear plane angle, and alpha, of course, as I said that this is the rake angle, which is known because the tool is known, okay, to us. And therefore, the strain rate as well can be found out from here, from this relationship, all right. And now, that means these are the parameters which can be easily found out analytically after the FC and the FT can be determined from the merchant circle diagram. Rest of the things we will discuss in our next class. Thank you for your attention.